Here we go. Cool, we're back. Lovely day to be a mushroom, a very wet day to be a human. So at least as far as like schedule and kind of cadence of the class, we're in module 2, we're trying to wrap up with a project. But are there still questions about like visualizing and analyzing and kind of processing data? Yeah.
I just have a question about the project. When I try to run the cell, like the reading the data, it says that the time data does not match the format.
Oh, let's take a look at that. So depending on, yeah, like this one, right?
Yeah. So if mine doesn't come up with that, it just says value error. It doesn't match it to the ISO 867.
Yeah, mine says that too, and it depends on. It seems to depend on this date time, like which version it is. So this version that's on NanoHub seems to not want that ISO 8601 standard. So we can say, just figure it out yourself by just saying, like, take that date and turn it into a date time. And then all of our dates become, they're still listed as like year, month, day, but now the computer's storing them as an integer, and how many nanoseconds have elapsed. Time is weird. Like the more you try to measure time and synchronize it, the more you start to realize like things get pretty weird pretty quick. But that one, yeah, that one's a quick fix because sometimes date time is looking for that format depending on what version, and this time we don't need it. I'll check in, see where we're at, and see if other things are coming up. What is it? Oh, okay. Yeah. Oh, okay. Yeah. Okay. Yeah.
I have a contribution in Postmates.
Yeah.
Those, I've taken 2 ME3255s, and for whatever reason, it doesn't work with an optional concentration requirement.
Are they definitely in the concentration?
They're in this, just not mine. So like I talked to one of the like advisors on this undergrad office, and they said there's something we need to go in and make it like a grad sub or like do something in there.
I don't know. Yeah, so never
I
Oh, makeup. Okay. Yeah. Like, why'd you make it up?
Yeah.
Makeup. Yeah. Yeah. So it looks like your prediction. See how like all your like cloud of predictions are going up, but the actual complete sort of. So there's probably somewhere in there, usually that yellow line compared to the blue. Like it looks like a different distribution. Probably stable deviation. And maybe B is probably about the same. It's on that line where you have the T-price model. That's kind of the meat of varied curves. So you top three lines are equal RMG and the price location and scale that you're using to deviation. So whatever you have found, use that. Yeah. Nice. Yeah, exactly. So those are just like, I think there's usually every semester anywhere from like 5 to 10 sections. Sometimes they're like an undergraduate section, others let's try it out and see. I don't know. Oh, okay. Because I have to rewrite the whole course. Like I made it when we were still in Google. Everything. I've been wanting to change the language on Julia because it is a nice graduate language. But it's different. Build a little bit now. Yeah, it would be fun. Try new language and then do some multi-body I wasn't worried about someone else would take that. That looks better, right? Yeah. Yeah. So at least like bare minimum is just find similar to how we made like that bubble plot. Like we weren't doing a lot of like icon coding, it's more of figuring out which parts we needed, just put it all into one analysis. So you gotta do that here. And then the next step is really like, what is this? Is it good? Is it bad? But you can say either one. Like it's good model. Like what are the characteristics that you can say it's not good? Too much variation. Very accurate. Very precise. Accurate and precise. Something. Quantify what you can use it. Or even like it's called like training and testing data. You take the first 4 years training model to get mean standard deviation, extend it into the next 2 years and see how well see it's like hundreds of thousands of rows. So it's already a population of people, and they're organized by tickers. Yeah. Okay, so you just have to pull the business. Yeah. So if you grab just that subset, yeah. All right, cool. So we figured out the first troubleshooting error of like, hey, if you ask for a certain format, it's going to say it doesn't match this like ISO 8601. So we figured that out. We just ignore it. Now we have a data set, and I'm going to just restart run all and do a tour of like outputs that we see. Coming back up. So the first analysis that's here, and I'm kind of walking through this to answer some of the questions that I heard as we were kind of looking at this data set. First analysis shows like the blue curve is all of Google's opening price like data points from 2010 all the way to 2017. The red curve is just a subset where I said, all right, January, when I get to, what was the date? Oh no, sorry, March 1st. So March 1st, 2014, that's the end of my data set. And what I'm doing here is called like building a training data set and a testing data set. So I split the model, I split like my data into a red curve and a blue curve. And I could extend my model into the blue curve and see how predictive it is. So I train it on the red curve, test it on the blue curve. And it's really nice. That's a great standard practice when you're building models, especially if you're not building like physics models. If it's just like a statistical, like, hey, I threw a whole bunch of variables in there. I don't know what any of them mean, but look at how good the curve fits. It's like, all right, well, remove 20% of that data and see how well it fits now. So that's kind of what I'm doing here. And then, so the general idea of like a random walk is that every day the change in price is random. Like maybe the randomness has some distribution that we can fit it to, but that's the general idea. So looking at this like blue line, do we see randomness or do you see a trend? Like, is there something changing in this change in price? How do you know that it's like a random signal and not like an actual signal? It's kind of a weird question. How do you know what randomness is? And no one ever had static on their TV. Did you ever have static on your TV? Yeah? Like actual like blue and black scan? Okay, yeah. And like, yeah, back when I was like a toddler or something, I don't know. Pretty soon people will be like, what are you talking about? The blue screen of death? Like what? But like that static and that like roar, there's like, maybe there's an average signal to it, but there's nothing predictable about it. Like, and that's kind of what we're seeing here with this data, is like, it's just a whole bunch of randomness, like up, down. And again, like, it's got some kind of average. The average is pretty close to 0, but, and then it's got lots of changes. So that's why I'm plotting this, to show, like, yes, the changes in price are random. The difference with that is, like, if we look at this, I can't say that this is random. There's something distinct. I don't know what it is, like maybe it's a really high order polynomial, or maybe it's something like outside the scope of like what math can describe, but there's some kind of function versus changes in price that are all up, down, up, down, up, down. Yeah, and even the frequency of the ups versus downs, like I don't see anything that's like once a month there's a $60 spike. It's like there is a $60 spike, but it's not predictable. So since it's random, let's do some stats on it. You can figure out it's got an average, it's got a standard deviation. Best first guess of something that's random with an average and a standard deviation is normal distribution. If you want to get more involved, you can start looking at other statistical distributions, but it's the only one that we've looked at in this class, and it's really powerful because it comes up almost everywhere, and sometimes it's log normal instead of normal, but even that is like still fitting like normal distributions. Here, if we squint, the red curve looks like those blue bars. And maybe if we had more days, it would like fit more directly in there. And now this is the real, like, there, let's come in here. These 3 lines are the real like meat of our Monte Carlo model. We're creating random numbers, so we create a random number generator. I'm using a seed of 42, so it's always the same model every time I run it. I create 100 different versions of this Google, like price changes. Then I say that the changes in price are going to follow, it's going to be the same shape as my Google models, but it'll be N models, so it'll be, if I'm trying to fit like 1,000 days, it would be 1,000 by 100. If I wanted 2,000 models, it would be 1,000 days by 2,000 models. And the location and the scale, that's my mean and standard deviation. I don't know why they don't call it mean and standard deviation, but that's what it is. So location is your mean, it's like the location of your distribution, and your scale is a spread, like how much it spreads out. And then I'm pretty thorough in my analysis, especially when I'm using Jupyter notebooks and kind of like thinking through what's going on. So I create the model and I check one version. So this is like model number 1 versus my histogram. Those should match basically the same. Like they should be the same curve, this red one and your yellow one. And then the blue one is actual measured changes in price. That one's got to be different because it's different. It's real. It's not like a fabricated version. So now my prediction is, if I have a change in price for every day, if I add up all those changes in price, really it's just like an integral, like the integral of the change in price over the day or just gonna say 1 day times change in price is new, add that to the original, so sum all those changes. I get this huge cloud of 100 different predictions. So some of them say Google should have been $2,100. Others say it was going to lose money and go from 600 down to like 495. But on average, the thing that the stock market did is what my models say. And again, Monte Carlo, it's an averaging thing. Like we want to predict a whole bunch of stuff, take the average and see what happened. And that's what I'm doing here, is showing like what are the average and standard deviation for all my predictions from every day. And I'm skipping this : skip. It's a fancy way of saying like, all right, give me every 100th, show me every 100th value. If you want to see what other ones look like, you could skip like every 10. Gets a little harder to see the data behind it because it's, I'm looking at that, every 10 days, but I'm looking at years worth of data. So I thought 100, or you could try half of that, like 50. If you want like a little more, but 100 or 50 or something, so you can still see like what was the spread of all of your models and then what was the actual New York Stock Exchange, Google data. And as far as like getting the model, getting it to run, that's it. Like the first steps are always look at the data, figure out what format it's in. Next step is start processing somehow. So in this case, I looked at the changes in price. Then I wanted to make some kind of prediction, so I thought Monte Carlo, random, since it's random, I'm gonna randomize it and look at what happens. So then the next step here is like, what is this model? Is it good? Is it bad? Can you use it? If you do use it, what are the things that you have to worry about? Like why does it work, or why does it not work? So that's the kind of the next step for you. And yeah, we can talk about that if you have some ideas or some things that you're thinking about. So you'll do it on your own data set. I listed out like all the different stocks in this New York Stock Exchange. It's all the same date range. Some of them didn't exist at certain year, like up until a certain year, but you'll do same analysis, but you're still trying to figure out like how do you quantify like what's good, bad, predictable, not predictable, like how do you use this thing? So that was a quick tour. Well, not so quick. That was a tour. So one of the first things that I was doing here was splitting it up into like training and testing, and this is why. It's like now I've got 4 years of data where my model was trained on all that data, so it won't be perfect, but it'll do its best job of like fitting what's there. So I could use these red dots to kind of interpolate between each of those and say like, yeah, for the most part, this is what happened in those 4 years. Just copying. but what's going to happen in the next 3 years? Is my model gonna drop? No? Why not? Yeah, so like there's something that happened there, and yeah, and I think that was the year that like Google split into like Alphabet and Google. They kind of like took all the shares, went from 1,200 to like 600 and 600, something like that. So that one, and all we're doing is looking at historical data. We're not like factoring in like newspaper headlines and these kind of things. So yeah, as far as like what is my model gonna do? It's gonna keep saying it's gonna go up. And it's not wrong, it does keep going up, it's just that it's going up down there instead of up there. So maybe I could have said like, at this time, split it, and then keep going, but. So this is one of the more like extreme cases where like the model is not going to fit the future data because there's this big drop. Do you know what the slope of this line is? It's not like exactly a straight line, but it's pretty close, right? Like it looks like every day things kept increasing, at least for the model. Like the reality was that it went up and down, but do you know what that slope would be? Thinking about it. This is a good number to have, like especially if you're trying to say like, I want to predict, like if you know what the price is, if you know what it is here, how do I predict the next day? Like, well, take the current price, add a slope times the number of days, and that's my new prediction based on like this current model. So that's a good number to figure out. Good like quantifiable. Like we have that number. It's in our notebook. It's somewhere in there. What do you think that number? Well, I'll leave this one up. So what do you think that number is? Yeah. Can't spell. Yeah, so this slope is that when we did all that analysis of like, all right, let's take the difference and then we'll take the average of the differences, take the standard deviation. The slope is that mean of our difference in price. And that's kind of where we end up. That every day, if we said it's gonna, our average is like 5 cents a day of increase, and that's what our model is gonna say. Like every day it's gonna increase by 5 cents. Yeah.
So the stock that I picked, from like the 2010 to 2017 range. So I just put it in based off like the code that you had.
Yeah.
Basically from like 2010 to 2015, it like doesn't grow at all. And from 2015 to 2017, it grows like an insane amount.
Is this NVIDIA?
Yeah.
Yeah.
So should I like look at the whole data set, or should I just look at like the last 2 years, because that's where like the growth is, and that's what I want to project into like post 2017?
Okay, yeah. So the question came up of like what happens when things look like this, of this this is a very different, like from basically 2016 onward, something very different changed, where every day the price was like almost like growing by like a factor of 50% or something, which it was crazy, and it's still kind of crazy. Like NVIDIA was nothing special back in 2014, back when I was like a grad student. It's like graphics cards were sort of like, yeah, you could get one. It's like $50 for a sweet graphics card. It was not a big deal, and now all of a sudden, you can't get a graphics card. They're just so expensive. So the question came up, like, what do we do with this data? Can we predict it? My guess is that, like, if I went 2010 to 2014, kind of the same red line.
Yeah, it's hoping that like the price doesn't change.
Yeah, because it goes from 20, and by here, 2014, it's the same price. Like nothing really happened, and that's what our model will tell us. You could just take like 2015 to 2016 and see if it'll predict the next year.
Can I do like halfway through 2016 and see if it'll like project the final?
Yeah.
Because that's what we want to see, right? We want to like see that it will project the final stock price by the end of 2017, if I guess.
Yeah. And what you can do, like this is kind of old data at this point. It's almost a decade old.
Yeah.
Like there are current prices. You could take just this last year and say, can I predict what the price was in 2018? And there, like, you would look it up and say, like, all right, in 2018, price was 200 or something, and my model says it would be, yeah, average growth times number of days to get there, and that would be, say, it says 200, but yours says like 350 or something, so you're over exaggerating it. But to answer your question, like, is there a right way to do it? It's like, if you want it to predict a given date, then that date should be like the last day of what data you had, because that's going to be the best measure of like how to get there. And that's kind of what we see here, is that like it wasn't very accurate. It's not inaccurate. Like it's usually within one standard deviation of this black line, but really my mean matches that last value really closely. They'll probably be within a few cents of each other. So if you're looking for accuracy, then include the last data point as what you're predicting, but then it's sort of like, what was the point? But then extrapolating is the next kind of step. Yeah, NVIDIA is a funny one to try to analyze. Yeah, and here I'm just taking like March of 2016 and only considering that. And I can, Yeah, and here, like even this one's kind of interesting too, because in this case, where I'm looking at the change in the price, with Google, it looked like random noise, like it was just static of a signal. But now we see something else, like it's not quite random. Like there's less randomness at the beginning than the end, something like that. Yeah, and as you're thinking about like the thing, so some quantifiable things that I get out of this is that this is not a completely random signal. So if I ignore this and say it is a random signal, then that's a caveat to my model of like there is some kind of trend in my change in opening price, but I'm trying to see, can I predict with a random model anyway? And the trend here is like the range, like, or the magnitude of the signal keeps growing over time. Like it starts at $1 or $2, and within a year it's up to $6 to $15. It looks like it's kind of growing in amplitude.
Well, then I guess it's not really an issue.
So because I split this model and there's some data that was used in the prediction, some data that was not, I can extend like how far this goes by changing like how many days I'm including. So right now I have two data sets that are all describing Google data, like Google data and then Google data pre-2014. So this price, like when I call it price model, so up in here, instead of saying like I want to look at just that 2014, that pre-2014 data, I could create random data for everything and just say like for every day in Google's price history, make me a random change in price. It won't really change this distribution because it's still the same mean standard deviation. It'll break this because now I need to match my X and Y data, but we can do that. And I think, yeah. So now I'm taking just that pre-2014 data, going into the future, Google data, and then we want to get rid of this. Oh, I want to get rid of this. And now I'm looking at like an actual graph of what I had predicted just by hand of like, all right, here's my average slope. This is what's going to happen. And now I've got like a real quantified like visual graphic of what the prediction is and what the error was. And like like I have this price model average and price model standard deviation, I could look at that stuff on its own, right? And what is it called? Date. Like this is the average price, like the actual average price that I predicted, or I could look at the standard deviation. Standard deviation is kind of like growing this way. And the thing that I like, Google data. I took the opening price, subtract my average prediction. What is this number showing me? If I take the actual measured price, subtract the average price, what should I put on like the y-axis? What is it actually describing? Yeah, that's my model error of like every day I predicted this was the average price. This is how wrong I was for every day. And if I compare that to like standard deviation, I could get like a relative value, like how wrong was it? And I know we're out of time. And here I can see like, was I 1 standard deviation away or was I 2 or 3? And for the most part, I'm always, at least everything in my model is like around 1 or 1.5. And then even in the future, I'm like 2 standard deviations away. But anyway, some different ways. Thanks for the extra couple minutes, and then see you on Wednesday.